So again, my name is Colin Gensch. I've been involved in making blower doors and such since 1980, so 32 years experience. I've been very heavily involved in large building testing for the last 20 years, I suppose, and doing tests in large buildings for the purpose of fire suppression containment since the mid-80s. So we have a fair bit of experience with testing large buildings, and the only manufacturer that's really bothered to put effort into making systems specifically designed for testing large buildings, extra power, more range, faster response, that kind of thing. Most of the large buildings in the UK, for example, which is the first country in the world to have a testing standard for large buildings, are done using the system that is shown in the picture there, which is called our QMG system. It's a hard panel, holds 3 fans. It's probably the most economical way per CFM to blow air. That's why it's pretty popular. So we have a pretty chock-a-block full presentation today. Since a lot of you are familiar with the USACE, Army Corps testing, and so on, there's been around about 300 buildings tested, and the requirement, as you know, is 0.25 CFM per square foot, 75 pascals. The average now, over the last 3 years, I believe, is running at 0.17 CFM per square foot. They've actually got buildings down to 0.04 CFM per square foot, which is about more than 6 times tighter than they have to be. The interesting news is when testing starts, the quality of construction improves dramatically, and in some cases people have reported that the cost of construction is no more than it used to be before, because they're getting introduced to new building techniques and new products that they weren't using before that are faster, more effective, and so on. So this is the first Guinness record that one of our fan testing companies in Europe achieved about 1.5 years or 2 years ago. Shortly after that, they tested a building that was 3 times that size, which they didn't apply for Guinness World Record for, which I guess maybe a bit of fun and games. But that's an idea of what a series of QMG stacked up looks like, and all the controls down here and so on. So that just gives you an idea of where we might be going, and then now we'll talk about how we're going to get there. So the simplest building that we can consider is just one big box, and pretty much doesn't matter where you put the fans. You can put them anywhere, and you pump up the box, you measure the pressure, you measure the pressure anywhere, and so on. So that's pretty simple. That's kind of what testing a house is like. You pressurize the entire house, even if you've got a partially open doorway. There's very little volume behind the doorway, very little surface area to leak, so you pretty much get exactly the same pressure instantaneously everywhere in the house. So as we move on from there, we get more complicated situations, and I'll just look at our next slide here. There we go. So this is what a connection looks like in a large space. We're doing all the connections from outdoors simply because there's more room. Normally you do these tests are from inside, but you should be able to do them from either side. With our equipment, the red tube always goes through the panel, and here you see it going through the panel into the inside portion of the building like this. And if you're inside, the red tube still goes through the panel. And in that way, our fans are referenced, assuming that the red tube that goes to the red port is going through the panel. So since in this diagram here we're outside, the blue tube, which is the, I guess the positive side of channel A, is picking up the pressure outside. And here we've simply teed this off, so we've got a T on here, and we're picking up the pressure in 2 locations, like, you know, roughly to the extremity on one side versus the other side of the building. We're not going to get into a lot about the best places to pick up pressure. We're just going to look in this presentation primarily at how we should be making our connections. So here we've got, going to the fan, we've got this kind of orangey brown connector, which is the control going to the fan, and we've got a yellow tube that picks up the flow pressure, and we've got the green tube, which is the reference port. With this type of fan called a 3000 SR, SR for self-referenced, you basically can never make a mistake. You don't ever have to add a tube or whatever. The tubes are always there. You turn the fan around, you can do anything you like, and the fan is always reading properly. With other fans that, like our 1000 fan, for example, it needs to be referenced, and the gauge references itself internally. With a fan like a Minneapolis fan, for example, you're supposed to put a reference tube out there, and in our DM2, just like in the DG700, for example, it requires that when you're doing a pressurization test from inside, or what we call flow towards the operator, then that reference tube must be in place in order for the gauge to be reading correctly. And that's probably one of the single biggest mistakes that is made. And if you have any questions about that, by all means, you should take a look at our documentation that describes this in detail and the reasons why. But that's one of the mistakes that gets made. When we're using these self-referenced fans, we can never make that mistake. There are some interesting connection possibilities that happen when we're testing large buildings where the reference pressure is being affected by another fan. When we have these self-referenced fans, we never have to worry about it. So just a word on that. So this is one gauge hooked up, and here we're kind of breaking it down, and we're looking at, again, we've got the gauge outside, we've got the red reference tube going inside, we've got one large volume, so we can pick up that pressure anywhere, it doesn't really matter. A good rule of thumb is if we've got one gauge, we probably need to pick up one pressure inside the building. You know, by the time you get to 3 or 4 gauges, you probably need to pick up pressures in 3 or 4 locations. But usually one fan is doing one floor, or it's doing a volume of building that's small enough that a single pressure pickup inside the building will work. We can also, if we have to, we can tee them together and get some kind of funky little averaging system inside the building, but usually it's not necessary. So this is us outside the building, and this is what it looks like if we're inside the building. So we reversed everything. You'll notice that now the gauge is inside. The red tube is running through the panel, same as it did over here, but now our pickup points outside are red tubing as opposed to blue tubing. The reason why we color code them is so that you can't make a mistake when you make a connection. As long as you put color to color, you're okay. As long as red tube goes through the red panel, you're always okay. We show over here that these tubes should be roughly about 25 feet from the building. The reason for that is that when the wind blows, it tends to impact the wall and create a pressure field around the building that fluctuates much more than it does, say, 15, 20 feet, 25 feet away from the building. So this is the area where you get the least pressure fluctuation due to wind, and it's something that anybody testing large buildings needs to spend a fair bit of time experimenting with, putting tubes in different locations and watching the effects. What you can do to, I guess, demonstrate to yourself the results is to take, say, our data logger, which is a free piece of software, and put it on your laptop and run a single tube, let's say, next to the building, and then on channel B, with channel B set to pressure, log what the pressure would be with a teed connection with the tubes far away, and just watch it. Let it run for 15 minutes or so and watch the difference in the wind pressure with one tubing setup versus the other, so you can get a feeling for it when you put the tubes in certain areas, what the results are. With the data logger, it spits out an Excel file. You can graph it. You can take a look at how that moves up and down, and it's a great exercise to train yourself on the effects of wind. You will notice the effect of winds when you're taking results, and you'll get much, much better results if you're able to place the pickup tubes in the right locations away from the wind. I sometimes would take a T and put it on the end of this blue tube and a T on the end of that tube, and maybe put, let's say, 1 foot of tubing on each one, so that each of those tubes is facing an opposite direction. So no matter which way the wind blows, it tends to kind of compensate itself to some degree. Would also want to cover that up. If I take a flat object like a piece of 1/2-inch plywood or something, say 2 foot by 2 foot, and throw it over the top at the end of the tube, what that will do is it will prevent the wind from blowing right in the end of the tube and having that velocity pressure turn into a static pressure inside the tube, which will cause my readings to fluctuate due to wind. Person asked a question about the floor area or enclosure area. There are so many different areas that it does get confusing. The U.S. Army Corps requirement of 0.25 CFM per square foot is enclosure area, which includes wall, floor, ceiling area that's facing the environment, whether that environment be air or dirt. So if we've got a building that's on a concrete slab, we count that as an area. Some standards only count areas that are facing air, not dirt, but most of our standards look at the entire enclosure area, no matter what it's facing. Now, as far as kind of more complicated questions, some of them are a little bit more involved and kind of more specific. By all means, send us an email. You can send one to me at Colin, C-O-L-I-N, at retrotec.com. We'd be happy to chat with you about what your specific needs are. So let's carry on to slide number, slide number 8, I guess. So this is just kind of a review. Read building pressure, flow reference. I've already gone through that, so we can hippity hop along here. Now, what we've done in this slide here is we've shown you how we've taken this kind of confusing mass of tubes, which is 1, 2, 3 tubes and one wire. There might even be a charging wire in there as well. And we've cleaned it up and put everything into one umbilical. This makes the setup much easier since you attach the umbilical on one end to the gauge and the other end to the fan, and you're good to go. So those of you who use our equipment are familiar with that umbilical approach. This is what the umbilical connection looks like on a 1000 fan, with the umbilical here where everything all wrapped together comes up to the fan. There are far fewer tubes in that particular one, and the yellow one is always Ref B fan, and this is the control cable. So we've got control and we've got pressure. So control signal goes in and a pressure signal goes out. This is power on the other side. Our manuals do a pretty good job of showing this, and here we've got an umbilical that goes between the top of the fan and, in this case, the variable frequency drive. This is one of our older units. We have pictures of our newer ones, which we'll get to later. So the first connection that we would want to take a look at is how are we going to control our fans. So in this case, again, we're standing outside. We've got gauge number 1 that we can call our master, let's say, and this master is basically enslaving all 6 fans. So our control signal is essentially going from 1 gauge to 6 fans. So all 6 fans are receiving the same instruction, which maybe go to 50%. They all go to 50%. Those 6 fans are acting like one big fan. They just happen to have 6 separate fan blades, so they're all going in concert up and down together. If we were to, in this situation, send 6 control signals to those 6 fans, if one picks up speed a little bit, another one might slow down, and what you can get is a situation where one fan might stop completely and the other fans have taken over the whole load, and it just becomes a big hole in the building with regular, what I call house testing fans that use permanent split capacitor motors, PSC motors, if they stop and there's enough pressure in that building, that fan can actually start spinning backwards and even run backwards. And I've had situations where I got 5 fans running forwards, 1 fan running backwards, and guess what? That building showed as being a lot leakier than it actually was. So that's, if you test long enough, you will eventually find that if you use PSC fans, which is one of the reasons why we developed the high power fan for large building testing. Is one of the features that you will never get the variable frequency drive fans running backwards. But house testing fans, yes, they'll run backwards. They're not really designed to be controlled for speed, and it's kind of like the analogy would be controlling the speed of your vehicle by running the engine at full speed and stepping on the brake. Yes, you can control your speed, but it creates a lot of heat, and you'll notice that these PSC fans, some of them tend to heat up, whereas these fans, you can run them for 24 hours at any speed, they'll never heat up. So, control signal, one gauge which we call the master, it controls and enslaves all these fans. So you wonder, well, what the heck are the gauges doing there? Well, we'll get to that. Now, here we're looking at the flow pressure signals to the gauges, which is quite different. In this case, we've got a flow signal coming off each one of these fans, which are slightly different. They're all kind of approximately the same because they've been told to go to the same speed. But the flow signals coming off them will be slightly different. But the important thing is here is that the flow signal is not really, in this case, controlling anything. It's the result of the control signal going out, the fan going up to speed, and what comes back is, oh, I'm giving you so much flow. So this is the measurement flow circuit. In each case, it's going to channel B of these gauges. And the way we configure our systems is one fan, one gauge. What that enables you to do is to break your system up into as many pieces as you want. In this case, if we've got 6 fans, we can do 6 separate tests. We can do 4 here and 2 there. Any permutation or combination of those can be moved around, and we tend to keep our fans and gauges together as sets so they can be used in any combination. And that's what we're doing here. We have some kind of control signal that's been sent out there, maybe 70%, go to 70% speed. What's coming back to the gauge is the flow signal, and it's showing what the flow is. Okay, now we're looking at the building pressure. So we're looking this one layer at a time. We looked at the control signal. We looked at the flow signal. Now we're looking at the channel B signal, which is the pressure that we're achieving in the building and the pressure we're picking up outside. Now, what we encourage here is that we want each one of these gauges to receive the same reference pressure. So the reference pressure, maybe reference pressure is a bad name. The outdoor pressure should be the same on each and every gauge. So what we've done is we've picked up our pressure with the blue tube in 2 locations. We've teed it together. We've manifolded all that together so that each and every gauge is receiving exactly the same pressure on the input port of channel A. Okay? So in this case, we've got a red tube which goes through the panel, and that's picking up pressure here. Another red tube that goes through here picks up pressure here. Another red tube goes through here and picks up the pressure there. And we've taken that pressure and we've just copied it or paralleled it up so that all these are getting the same pressure, basically. I'm not sure why we did that, but in this particular example, we don't really need to measure pressure everywhere in this box because it's going to be the same everywhere. But we do need to tell the gauges what pressure they're receiving. Our fans are back pressure compensated. That means that if the pressure that is on the other side of the fan is 0 pascals or 10 pascals or 75 pascals, there's a correction on there of 2, 3%, 4%, whatever, that makes the fans more accurate because it knows the back pressure, and we're the only fans that back pressure compensate. So this back pressure compensation, which is information that we have already, allows us to take more accurate flow readings. And so here we are measuring the pressure on 6 channels, which of course will all go into our fantastic software and be recorded automatically. There are still holdouts out there that want to write them all down, but trust me, once you get beyond 2 gauges, you don't want to be writing results down. Tests of this nature, we were testing something like this, we would probably be taking several thousand data points. So now we want to go into the individual control versus common control. Now, on the previous example here, we had common control. So we'll just back up to here. So common control means that each one of these fans is receiving a common control signal. So these are all acting as a unit. We may not always want that, and we need to be able to recognize when we want common control and when we want individual control. The example I mentioned earlier, where one fan has got its own flow signal, it's got its own control loop, it could actually start running backwards, so we don't ever want that. So let's just advance back to where we were and take a look at individual control. I guess I'm kind of starting this with different pressures that we might see inside an enclosure and why we might see them. So in this case, we've got a relatively small hole here, and we've got, let's say, 75 pascals here, and we've got 72.4 pascals over here. There's a difference there of 2.6 pascals. We're not actually achieving a common pressure inside the enclosure. Let's see if we have another diagram that will show this a little bit more graphically. So in this instance, we have one fan down here, and we've got a pressure there of 75, which is where the fan is blowing. So if we're controlling to that, we're controlling to 75. By the time we get up to here, we're at 70.1. By the time we get up here, we're at 68.1. So what do we do about that? And here we're controlling to the pressure on the mid-floor, so this is over pressure, this is under pressure. So one way to do that is to try and distribute the blowing power around the building. Very commonly, we will have a stairwell at either end. So often the stairwell is a really good way to drive the airflow up into the upper floor. So we've got it coming from 2 sides. If we put 2 fans into one stairwell here, we would get excessive pressure drops inside the stairwell, so the pressures up at the top would be less than that. I recall the test that we did, it was a 3-story building. We had 50 pascals on the main floor, and we had something like 25 pascals on the top floor because we didn't have enough stairwells open to the top floor in order for the flow to get there. So in this case here, we need to have probably individual control, since each one of these fans is controlling to its own pressure. So if the pressure was a little bit high on one end of the building, then on this end, then this fan would take care of it. If it was on this end, then this fan would take care of it. I can't remember what this was there for exactly. So here's an example of what the connections might look like. I know this looks like a bit of a spaghetti forest here, but this is common control and this is individual control. So let's just break it down and see if we can figure out what's going on here. Okay, first of all, common control is we have all of our fans in one place. We want them to receive a common signal. 1, 2, 3 fans all in the same doorway. So we have one control signal coming out of this gauge number 1 going into the splitter. We're taking that signal and we're sending it to 1, 2, 3 fans. So all these fans go together. So that's common control. This is individual control where we've got 1, 2, where we've got 1, 2, 3 fans in 3 separate doorways. It might be on 3 separate floors inside the building. So they have their own pressure that they're creating in their own area. So in this case, gauge number 1 controls fan number 1. Gauge number 2 controls fan number 2. Gauge number 3 controls fan number 3. And in our training courses, some exercises using our simulator where we simulate this, where you can actually experience common control and individual control and see what happens when you get them mixed up. And then there's a third one, which is hybrid control. There's actually a fourth one also, where you may have 2 banks of fans on each end of the building. Each one of those banks is common, but they have individual control with reference to the pressure they're controlling on their end of the building. I think I have a diagram that shows that later that will make that clear. So what this would look like with the DM2 configuration, for example, is we have the gauges which are close to the computer in this case. So the gauges go into a hub, the hub goes into a computer, so it looks at all the different fans we have out here that could be 20, 90 feet away, that kind of thing. So here we're actually extending the tubes from the fan all the way to the gauge. So that's the way we used to do it. This is with the 3350 control. So do we have common control or individual control? So we have a signal coming from this gauge. It says control. It's running into this fan. And the new controls all have the ability to daisy chain the controls together. So the signal comes in and then comes back out and into the next one, back out into the next one. So all 3 of these controls are receiving the same control signal. Each fan receives the same control signal. Not necessarily that the flow going through the fan will be the same. So the flow signal comes back through here to its gauge. This flow signal comes back through here to this gauge. And notice here in this diagram we've shown this control connection is disconnected. This gauge is not controlling anything. This gauge is controlling everything. So this is our pre-2012 setup. So let's take a look at what we're doing now. Hopefully. Here we go. You can't actually see it so well in this diagram because of the proportions, but here the tubes between the gauge and the fan are relatively short, 15, 20 feet, that kind of thing. The distance is all in here. That's why we say Ethernet cable up to 328 feet from the router. So here what we do, instead of running tubes over these long distances, we're running Ethernet cable. So through this Ethernet cable we can put 24 fans, 100 fans even. I was told we could put 100 fans through it. I think we tried it with 24 fans and it worked fine. These gauges are capable of putting out, I think, 8 readings a second from each channel. So a fairly high data flow rate, and all that is quite easily taken care of by one Ethernet cable. And standard Ethernet cables you can get at any electronic supply place. So that enables you to hook up these gauges to this computer, and we could have another mirror image of this on the other side, so we could have another 3 fans off on the left side, so that we've got 3 fans on one end of the building, 3 fans the other end of the building. So again, common control. Each one's receiving the same signal. The difference here is the length, the distances between the gauges and the computer. It's all in this cable. I wish I could make this cable look longer, but this is where the length is. Okay, now what do we have here? Well, we have the same gauge. This is our DM32 here with the same connection, and here we have individual control. So this gauge is controlling this fan, this gauge is controlling this fan, this gauge is controlling this fan. Okay? So in this case, these fans would have to be on, again, separate floors. We might pass these through a door panel. I would be inclined to want to manifold these together once they got outside so they were all receiving the same signal outside. The pressures that we would be picking up from these fans would be picked up from the blue port on this gauge, which is just kind of where the gauge is. You may want to extend that somewhere else in the building, away from the fans, but essentially that's what's going on there, is we're actually picking up the building pressure in 1, 2, 3 locations, and we're going to be commoning the outside. If we were outside the building, then these tubes would have to go to separate floors if it was, let's say, a 3-story building. So you can create common control simply by wiring it in such a way that one control signal is daisy chained into all 3 fans. You can also make the control and you can make the change in the software where you have individual control cables going to each fan, but you simply uncheck the individual control box, which means unchecked is common control, and that means that the number 1 gauge that you've chosen is the one sending out the control signal. So this is global, meaning it would change the signal going to every fan that you had on your network. Would be either individual or common. In a lot of cases, you want to have individual control, meaning the software is controlling the East Bank and the West Bank individually, but yet the fans within that bank were commoned, if you know what I mean. And the best way to get a handle on this is to go through our exercises on that so you can experiment in a relatively small space and you can see the effects of individual versus common control. What you don't want to do is to get into a great big huge building test with fans running and roaring all over the place and oh my God, this fan's going backwards and this fan stopped, and it can be really crazy. So you really have to get a handle on this, and if you haven't, you need to do that before you get onto into a job site situation. So here we have a situation where we've got outdoor balconies, let's say, and we want to test the entire enclosure leakage, and we can stick a fan on each floor. So be interesting to have you consider, do we want individual control or do we want common control? Since the results of the flow from this fan aren't felt very much in this space, we want individual control, so each fan is controlling its own space. Okay? This is actually a pretty common example of what you would need to do to test, say, row houses where you wanted to eliminate the connection between the units so that the pressure across these units would be close to 0 if each one of these was set to 50. Now what would happen is they would all be receiving the same control signal or set point. They would all say, go to 50 pascals, go to 50 pascals, go to 50 pascals. The signal that would come out of the fan that would cause it to go to 50 pascals might be different because this unit is probably a lot leakier than this unit. This unit is leakier than this unit. So this fan might be at 60%, this one at 30, it's at 25, this might be at 80% to achieve the same pressure in those results. So that's where individual control would come in. So here we have, again, we're outside for clarity or lack of clarity. We have 3 individual pressure hoses, whatever, inside the building on 3 separate floors, picking up their own pressures. So we can simply go to set pressure 50, set pressure 50, set pressure 50, and see what the effects would be. So each one of these gauges has its own control loop, it's controlling its own fan, and it's fine. If you had, let's say, a great big opening between these 2 floors, we might want to common these 2, because pressure in here will also pressurize that. Generally, if you've got 3 enclosed floors, you can get away with individual control or separate control. Guess the same thing. But don't be surprised if there is an effect. In our building, we were a 4-story building. What was happening was the fan on the top floor kept getting slower and slower and slower and slower. What was happening for some reason is there was a massive connection between the 1st floor and the 4th floor through the HVAC or whatever. So we got to the point where the fan on the top was barely running because it was all being supplied from the flow we were pumping into the 1st floor. So that was a case where it wasn't obvious that there was a connection. It's a concrete building. We're thinking, hey, you know, we have to have individual control. But in fact, that really wasn't the case. We'd almost be better off having individual control between the 1st floor and the 4th floor and running those fans at the same speed. But, you know, you have to see it to believe it, that at least when something is going on that's weird, that you can ask yourself the question, is that a control problem or is it some other kind of problem? So we have a fan on each floor. Again, this fan in the middle is probably blowing a lot less air, 10,000 CFM, 10,000 CFM, and 3,000 some odd CFM in the middle. So obviously the fan in the middle is blowing a lot less air. And in this case, we've got the stairwell open. We're sucking air from the stairwell, and we're controlling all of our fans individually. Sometimes we're in a situation, very common, the top floor can be very leaky. We have one floor, one fan on the ground floor, and we have insufficient pressure on the top floor. What we can do in a case like that is to run another fan on the top floor, and the purpose of this fan is it's not to measure flow. In this case, we're actually setting the pressure to 0 between floors, so that you can see now we've got this up to 75 pascals. So we're setting it to 0 between here and here. When this drops down, this automatically sees that there's a gap there of 7 pascals, and this fan is boosting the pressure onto this floor and increasing or actually decreasing the pressure in the stairwell in order to keep this floor at the right pressure. So this is what we call a booster fan, and it's not part of the flow measurement device. And we simply hook it up. We don't take the flow signal and put it into our software. All we do when we start is we go set to 0. And then the moment that pressure goes away from 0, it starts controlling on its own little control loop. But we do not measure flow. Here we go, set to 0. That has to be done manually. The software won't do that. You might even want to run that fan manually with a control knob, but we can make it run automatically. Another way to do this is to measure a floor at a time. So in this case here we're measuring the 1st floor, and we're using this fan to neutralize the pressure between these floors. So here again we're using the set to 0 function. That's to find out how much is this unit leaking to outdoors. So we've neutralized the pressure across here. So this is a way of isolating leakage in one part of the building. Sometimes this is a technique that you would use when you're doing an analysis of a very, very large building and you don't have access to a small piece of it. You can actually neutralize the pressure across the floor or across the wall using this technique. So in this case, we've got we're measuring the leakage of this unit, and we're neutralizing the pressure on the first floor and the third floor with the set to zero fans over here, and we're measuring the flow rate with this fan. This is kind of advanced testing. It's something that you really want to experiment with, so you're sure you're familiar with it, but we wanted to show you how you hook these things up so these connection diagrams are accurate. Measuring apartment air leakage. Okay, this is part of a study that we did here in Vancouver. These are the individual apartments that we measured. We measured the leakages on all 6 sides using the techniques that we showed you earlier. So the first one is what we call a simple apartment test. I just have to catch up with my multiplicity of slides. There we go. So this is what it looks like configured the way we have been showing it so far. Normally when doing a single apartment test, we're going to be in the hallway. So or in this case, this is a type of construction used in some parts of the country where there is an exterior hallway which is open to outdoors. So that requires its own particular technique. So in this case, we're measuring all 6 sides of this particular apartment, which is what you would do for lead testing or something like that. So we can say that all 6 sides of this test suite are at 0 pascals, and we're testing it at 50 pascals. This window here is actually the window open in the adjacent unit, not in the tested apartment. I notice there's some questions about individual control. The best way to learn about individual control is have it mess up. And you really have to purposely mess it up so you can see, okay, I messed it up, and now I went to individual control and I sorted it out. Or I messed it up and I went to common control and I sorted it out. If you don't see it mess up, you'll never see a need for it, so none of the stuff will make any sense whatsoever. But when it messes up and you're on the job, you go, oh my God, what the heck is going on here? You know, people say, oh, my fan needs to be calibrated. It must be reading wrong. Individual common control could be one of the reasons why. So here we're talking about zone isolation. We've got a different configuration of building. This stairwell or this hallway is inside the building. So again, we're measuring an individual apartment. It's got 2,000 CFM leakage to the outside. And in this case, we've got a fan that's mounted in the hallway. We're pressurizing the hallway to 50 pascals. So if this pressure or this flow dropped from 2,000 CFM to 1,800 CFM, guess what? There's roughly 200 CFM leakage across this particular wall here. So that's what that's told us. So that's one piece of the puzzle that we've been able to figure out. So this slide, let's see. Oh, there we go. Oh, I see. Okay. This is a bit fuzzy because we kind of blew it up and got a bit fuzzy, but it's the same one that we looked at before. I'll just go back and take a look at it to reorient yourself. So we're taking this slide, we're blowing it up, and we're asking ourselves, how the heck did we tube these fans together? So we're going to look at that in detail so you can get one tubed up right. So this gauge goes to this fan. We've kind of showed it stuck on top of the apartment just so but it would actually be in the hallway, but it's only this big, so you know we've kind of blown it up a bit. This gauge here is going to be controlling and measuring the flow through this fan. This gauge is not measuring anything except the pressure in the hallway. It's not measuring flow at all. It's a neutralizing fan that's neutralizing this pressure across this wall. Okay? So the first or the only measurement that we're making is a flow pressure measurement between the gauge, channel B, to the fan, that's going to tell you what the flow rate is through this fan. Then the red tube is going to go again through the panel into the apartment. It's measuring the 50 pascals. We got that. Channel A of this fan is measuring the pressure in the hallway at 50 pascals. So we go set to 50, set to 50 over here. The two of them balance each other out. What you'll notice is when this fan starts up, this one's going to wibble wobble back and forth until the two of them go into balance. And at one point they'll go into balance. Now here's the tricky part. What do we do with the reference tube? In this case, the reference tube comes out of each fan. It's not called reference on the gauge, but it's the other side of channel A, which is the blue tube, comes out, is teed together, and we're going to run that one outside. Outside in this case is actually, let's see if the door is in there. There it is. We open the door. Okay. Hallelujah. So in this case, we've got a blue tube running through the panel. Remember, this fan is only a balancing fan. This is the one that we're measuring. This is the only one that counts. So this is how we balance the pressure, so that the pressure in this stairwell is outdoor pressure. That's going to this gauge. It's going to this gauge. So this gauge is measuring the pressure between outside and the hallway. This gauge is measuring the pressure between outside and this apartment. And the blue tube, or the other side of channel A, is in the same place, and it's the same pressure. We don't even want to run these as two separate tubes because the pressures that they're at might be slightly different. If we common them together, we know that each gauge is receiving the same pressure, so that we know that this is 50 pascals with respect to outdoors, this is 50 pascals with respect to outdoors. Okay, any questions about that? Bob's asked a question about where does 75, 50 pascals come from. 50 pascals and 75 are very common test pressures. 50 pascals, very common for testing houses. 75 pascals, very common for testing large buildings. We did have a big, huge discussion as to whether or not we should test large buildings at 50 pascals. I think we made the wrong decision of going to 75. I think that 50 pascals is fine. So 50 pascals is a test pressure. The Army Corps requires results taken at 75. In fact, you've got to take them from, let's say, at least 50 or lower and 75 or higher. So you've got to take them over that range for error calculations and so forth. But they're looking for results at 75 for large buildings. Why is a good question. The standard says so. There was a feeling that when you're testing in large buildings that the baseline pressures or the pressures due to wind and stack and so on will be greater, which is true. I don't know that it's really the best choice, but every standard that you're testing to will have requirements that will get you to do different things. So 50 and 75 would be the two common ones. Okay, let's move on to the next slide. So previously we neutralized the pressure across here, and we were able to determine that the leakage of this wall here was 200 CFM. So leakage to the hallway was 200 CFM. Now we have very trickily opened up the door in the adjacent apartment, make sure the window's closed. So this 50 pascal pressure is flooded into this side, this apartment, same tubing hookup and everything. So at this point, this flow rate will drop from 1800 CFM down to 1500 CFM. So we can say the leakage through this wall here, from here to here, is 300 CFM. So I got that part of it. Let's see if we went farther than that. I think we did. So now we've opened up the door on the other side. We've gone down from 1500 to 1100. So we can say the leakage across this wall is 400 CFM. And using a similar technique, we can diagnostically find out where each apartment is leaking to. And it will characteristically leak between floors, into the hallway, to outdoors, to the apartment on either side, depending on the construction, and not necessarily even depending on the construction materials or the design. We've noticed that different buildings will just leak in different directions, and often that will tell you why they're having certain problems that they're having. It might be air quality, it might be this or that, but that tells you a lot about what the dynamics are between the units. My contention is ideally that each one of these units should be as isolated as possible from its neighbors for the purpose of energy, which is minor, but more importantly for sound, odor, pollution, that kind of thing. I think that these need to be a series of sealed boxes, have their own connection to outdoors for fresh air and so on, and I see a trend in that direction for new buildings where they're not reliant upon even an HVAC system that will be common to the entire building. Individual HRVs for individual apartments are starting to find their way into designs, and I think that that gets around a lot of the problem of how these buildings get all hooked up and what happens to one unit affects another unit. Earlier on, we had most of the people say that most of the testing they did is of the exterior enclosure. Now, I maintain, particularly for apartments with windows and balconies, you have no control over the exterior enclosure anyway, because people will keep their windows and doors open even if it's -30 if they think they need ventilation, particularly on the top floor where the people on the first floors are freezing their butts off and the people on the top are cooking and they don't mind having their windows open. So what happens is it throws the dynamics of the building off, it wastes a lot of energy and causes all kinds of horrible air quality problems. So let's see what our next slide brings. This is kind of a side view where we're going through a procedure of how you might possibly measure a high-rise. You could do a 20, 30-story building like this where you actually measure each floor individually, and you can go all the way up and down the building. Now, there are some common chaseways, elevator shafts, whatever, that would prevent you from, in some cases, from making accurate measurements, common exhaust connections that you might want to cover up and so on. This is the way that you can actually take a building apart and measure it floor by floor and see how each floor is working and what kind of connections are being made to other floors. So here we have a series of 3 fans running, and by turning various fans on and off, we can find out not only what the leakage is of this unit to the outdoors, but also the leakage between units from floor to floor. So we can really find out a lot by doing this kind of analysis. It's important that you get the procedure down of measuring the leakage between 2 units before you start worrying about doing 3 units or 4 units at a time, which is what we're doing here. So it's a matter of starting at one point and kind of moving forward so you can kind of increase your skills and use this as a powerful diagnostic tool. So here I'm showing the virtual gauge, and the reason why I'm showing the virtual gauge is that we are encouraging people that are testing large buildings to how did that happen? We're encouraging people that are testing large buildings to trade up to the DM32 for a couple of reasons. One is that it's very proficient at running over Ethernet cable over long distances. It has an Ethernet cable connection on the bottom. I think there's some kind of timing, annoying timing on this slide here that's jumping off the screen for me. Oh my God. I guess I'll have to keep defeating it all the time. So in this picture here, we have, if we're doing a test with 4 gauges, we can actually run a virtual gauge, because bear in mind, these gauges will be at the fan that might be in 10 stories away. I need to find out who put this wonderful feature in here so I can kill them. So this enables us to bring the gauges up, and whenever we're doing a test on a large building, we always want to run each fan through its paces, make sure it's connected, make sure the tubes are doing the right thing, that they're sending signals in the right direction, that we have a positive control, and so on. And you can do this by running a virtual gauge, and each one of these gauges represents a gauge that's somewhere in the building connected to it by Ethernet cable. So we can look at each gauge individually, we can check it out, we can check out its control loop, make sure it's functioning properly, and so on. This might be a leftover from previous. So here we show one coming up, and here 4. We can resize these and make them any size we want. We can put 25 of them on the screen if we want and kind of drag them around. They show you the serial number of the gauges, so wherever your fans are located, you can get like a little, create a little diagram for yourself that shows you where the different gauge serial numbers are located, so that when you come down to your unit and you bring them up on virtual gauge, you can say, oh, that's this one, that's that one, and so on. Once you're done with virtual gauge, you can shut those down, disconnect those electronically, or through the virtual gauge, or just close virtual gauge down altogether, and then allow fantastic software to pick up on those connections and run them into the fantastic software. So you can either do one or the other, but currently you can't do both. So the way we're tubing them up now, you actually have the gauges at your computer so you can look at them. And this is a way that you can, with the DM32 gauge, actually look at the gauge remotely and control it. It's two-way control. Whatever you do on the gauge happens in virtual gauge. Whatever you do in virtual gauge happens on the actual gauge. So it's two-way. You can control it from either end. If you get someone on the 3rd floor and they monkey around with your gauge, you can see exactly what's going on there. So I think it's a very cool feature and a great little training feature as well, but particularly on a job, you don't want to be running up and down to the 10th floor to find out what's going on with the gauge to see, well, gee, why aren't I getting a signal out of that? All that needs to be done in advance. So what I would do is, if I wanted to achieve, let's say, 75 pascals on the top floor, then I would run those fans manually up to 75 pascals to make sure they could actually achieve that, they were on the right range, and so on, before I went to the fully automated mode in fantastic software, where all these gauges and fans and stuff were going up, down, and all over the place. So this is the equivalent to having a control knob in front of you where you run the fan through its paces and go, yep, I can get 75 pascals if all these run up to speed, then shut them down. That way you know that when you set it on automated and you run this test for 15 minutes or whatever it takes, that you can actually achieve the test pressures that you want, and you know that in advance. Okay. Monitor, control several gauges simultaneously. This is where you get virtual gauge. Let's see. I'll have to try and back this thing up. On our website, you can just click on virtual gauge here and you go right in there, and it's a free download. It'll run on any computer. You can actually simulate the gauge, try out all of its features without even having a gauge. So you have the choice of simulated mode, which you've got a gauge that functions like a gauge, and you have an actual, I'm not sure what the other mode is called, but non-simulated mode, let's say, where you have the option of connecting to any of the gauges in the system. For those of you that have energy conservatory fans, our gauge does a great job of controlling them. We have an adapter which controls their gauge. So our control signal goes into the adapter, and then it's translated into a PWM signal that controls their fan, and the flow signals come back, and our software handles their flow signals correctly. It's the control signals that are a bit tricky. Flow signals, no problem. All of our software will work with any fan out there. So you can combine energy conservatory fans, Retrotec fans, Infotech fans, anything you want, as long as they're running on a DM32 gauge. A very cool little feature. Let's see what else we got here. This is fantastic integrity software. This particular test is shown being run with 2 gauges. You get a nice little picture of the building and so on. So it shows the fan serial number, gauge serial number. These serial numbers are all picked up automatically. There's space in there where you can show where the fans are located and so on. The great thing about this software, I believe, is that you set the parameters and it does it for you. So baseline, for example, you say, I want to take 12 baseline readings for 30 seconds apiece, and then I want to shut down and I want to cover my fans. Or I want to take 12 readings for 20 seconds apiece, and then I wanted immediately to start running a test. I wanted to run from 25 to 50 pascals. I wanted to take each induced pressure reading for 45 seconds. I want my criteria for attaining the desired pressure is that it be within plus minus 0.5 pascals, 1 pascal, a certain percentage, whatever the heck you choose. Once you set it up, you just press the button and it goes and it does everything for you. It makes the decisions. You don't have to control any fan. You don't have to make any decisions. You don't have to touch anything. It records all the data. If you do happen to get one test point which you don't like, you can go in there and you can repeat that test point. There's a semi-automatic mode. So if you have one test point where a door opens or something happens that you haven't considered, you can go back and you can repeat that point and put it back into the software. Once you've taken one point automatically, you can't manually go in and poke numbers in there. You have to take the rest of the points automatically, which is not difficult. Let's say you want to replace the point at 43.5 pascals. You just go back there, you rerun it, it enters the data, and away you go. Bear in mind, automatically, even though you may see a number of so many hundreds or thousands of CFM, it might have taken several hundred or even several thousand data points to make up pieces of data or readings to make up that one data point. And then according to the particular standard that you're using, in this case the European norm, it gives you the results exactly what that standard is asking for, the terminology it's asking for, and so on. It'll print a report in the terminology that it asks for. The report is in Word. You have the opportunity of changing the format of that, so every time you do a report, it generates it with your logo and your name or a picture of your dog or whatever you want, and so on. Once you get this set up, you basically push a button and everything happens for you. No decisions to be made and so on. This is about a 3.5-year development project to get this thing working.